Let's consider this series. It wouldn't be difficult to apply the ratio test or the root test to find that this series is convergent. What we're interested in here is the actual sum of the series. What does the series converge to? To find that out, we need to do a little pattern recognition. This series actually takes the form summation n times x to the n. N goes from 1 to infinity, or factoring out an x, n goes from 1 to infinity of n x to the n minus 1. So the series we're looking at here or here reduces back to the one we started with x equal to a half. Now, the last expression, where it should remind us of differentiation. And in fact, we've learned that as long as we stay inside the interior of the interval of convergence, we can differentiate power series term by term. So if I were to differentiate term by term right here, I would get n x to the n minus 1. It's true, the original series that I have right here starts at 0, but the very first term at 0 would be 0, with n equal to 0. So as long as we stay with the absolute value of x less than 1, then that equality is valid. Taking that back another step, we know that the inside of that series right there converges to the first term over 1 minus the common ratio, and we still have the differentiation outside. So simplifying this by actually taking the derivative, we find that we get x times 1 over 1 minus x squared. So I'll simplify that, or rewrite it, x over 1 minus x squared, and again that's under the restriction that absolute value of x is less than 1. So if we come back to our series, summation n goes from 1 to infinity of n, I'm going to write that as times 1/2 to the n. Based on what we just learned, that must be 1/2 over 1 minus 1/2 quantity squared. That's a half divided by a fourth, which is 2. And that's the sum of our series.